Unit 10, Worksheet 3, Coulomb's Law, Problem number 9. Two pith balls shown in the diagram below have a mass of 1 gram each and have equal charges. One pith ball is suspended by an insulating thread. The other charge is brought to within 3 centimeters of the suspended ball for a radius of 0.03 meters. The suspended pith ball is deflected from its rest position until the thread forms an angle of 30 degrees with the vertical. At this angle, the ball is at an equilibrium. There are 4 parts to this problem. The first is we're going to draw a force diagram depicting all of the forces acting on the ball. Second, determine and calculate the force of gravity. Third, calculate the electrostatic force. And then finally, part D, we're going to calculate the charge on the pith balls. So we need to make a list of what variables we know, and then make sure they are in the correct unit of measure. So we're told that our pith balls, which are going to be these two things down here, we have 2 of them, and they each have a mass of 1 gram. Now, that's going to be a problem because when we work with our masses, it should be in kilograms. So we're going to take that mass of 1 gram and then divide it by 1,000 grams for every 1 kilogram. So those masses should actually be 0.001 kg. Now we only need to draw a force diagram for the forces acting on the suspended ball, so we'll need to make sure that we use that mass when we're actually including our force of gravity. But we also have these other variables. One is they have equal charges. So instead of Q1 and Q2, we can say they both have a charge of Q. They're the same value for each of these 2 pith balls. The distance between them is already indicated for us, as is the angle. So now we can probably start getting started with these problems. So first is going to be part A. I'm going to do part A over on the right side of the screen, just so that way it'll be kind of easier for us to represent the forces acting on the charge that is being hung from the thread. So first force we're going to draw is our force of gravity pointing down. Force of gravity acting on the suspended ball, so I'm going to say that this is going to be Q2. Even though they have the same charge, I'll still designate the one that's to the left, Q1, the one to the right, Q2. We're drawing our force diagram for Q2. And then that's going to be acted on by the Earth. Another non-contact force that we have is going to be the electrostatic force that we have between these 2 objects. If they are equal charges, that means they're both the same magnitude and the same sign. So that should be a repulsion. So we're going to have an electric force pointing to the right, and that will be an electric force on charge 2 by charge 1. We don't have any other charges in this problem. We don't have any other magnets in this problem. So we're done with our non-contact forces. That just leaves our contact forces. Anything that's in contact with our suspended pith ball that is exerting a push or a pull. The only thing that we can see from the problem is the insulated thread. It is pulling up on the ball and is pulling up at that angle. So our force should match that angle. That will be a force of tension on charge 2 by the thread. So we have 3 of these forces, and because we know that this thing is at equilibrium, that means that our net force for this thing should be 0. So we'll need to break up that force tension into its component forces and then show our equivalencies to make sure everything cancels out. So we have our force of tension in the x direction that is equal and opposite to our electric force. We have our vertical component of our force of tension that is equal and opposite to our force of gravity. They're equal and opposite not because they are a third law pair, but rather because this is an example of Newton's first law of motion. If our object is at rest and remaining at rest, then the forces are balanced. So I'm showing that we have an upward force that is equal in magnitude to our downward force, canceling it out because there's no change in motion vertically. I'm doing the same thing horizontally because there's no change in motion horizontally. So this is going to be our force diagram. In fact, the way that we've shown it now means that I can probably erase that initial force of tension just to clarify my force diagram a little bit. We have just our on-axis forces. Force gravity down, the vertical component of force tension up. Our horizontal component of the force tension left, and our rightward force electric. All of them canceling each other out. For part B, we need to determine the force of gravity. So I'm just going to do that actually at the top of the screen because that's already where I have my mass. So force of gravity, it's 9.8 newtons of force per kilogram of mass times the mass that we have. So our force of gravity is 0.0098 newtons. Oh, and actually, that is also equal to our force of tension in the vertical direction because, well, those two things are equal because they have to cancel each other out. That's going to be important because we also want to quantify the other forces that we have here. That force of tension vertical is equivalent to this vertical component of a triangle that we have here. So that one should have a magnitude of 0.0098 newtons. This right here would be analogous to our force of tension in the x direction, and then the actual cable that we have here would be our full force of tension that we would be quantifying. That was the original force that we had drawn. I'm just shortening it a little bit just to avoid confusion with it actually acting on the suspended pith ball. But the reason why I'm representing this as a triangle is so that way for part C, where we are calculating the electrostatic force, we're going to be looking to quantify this value over here on the right side of our force diagram. But we can't do that because while we do know the radius, we do not know the values of the charges. So we can't use Coulomb's law to quantify that. Instead, we'll need to determine the magnitude of our horizontal component of the force of tension, and then set those equal to each other to determine what that electric force is going to be. We can determine that value by using our trigonometric relations from this triangle here. It's a 30, 60, 90 triangle. Our 30-degree angle is adjacent to our vertical component of the force of tension, 0.0098 newtons. And our horizontal component of the force of tension is on the opposite side. So for part part C, what we can try to do is we can use our relationship that has opposite and adjacent, or our tangent of an angle is equal to our opposite over our adjacent sides. Opposite is what we're looking for, so we would multiply both sides by our adjacent to get the opposite by itself. And that opposite right there is going to be the same thing as our force of tension in the x direction, which is the same thing as our electric force. So let's make sure that we can calculate that. Our electric force for part C is going to be equal to our adjacent side, the 0.0098 newtons of force, times our tangent of that 30-degree angle. And then when we look at that in a calculator, we get a value of 0.0057 newtons. Actually, I'm going to start circling things to make it easier. For part B, that's our value. Part C, this is our value. And over here is part A. Part D is where we're going to be determining the charge on the pith balls. That is where we can finally use Coulomb's law. The electrostatic force is equal to one charge times the second charge times the constant divided by the radius between them squared. I'm not saying it's Q1 or Q2 because this problem we're told they are equal charges. So if they're equal charges, I can just designate them as Q. I can rearrange this problem so that way Q squared is equal to Fe times R squared, all of that over Coulomb's constant. And then to get the charge by itself, I just take the square roots of both sides. And when I do that, I just plug in the values, and the charge I get is 2.38 times 10 to the negative 8th power coulombs for the units of charge, we don't know if it's positive or negative. And when we take the square root of something, it can be either positive or negative. All we know for this problem is that they are equal for both of these charges. So if one's positive, so is the other. If one's negative, so is the other. So part A is on the right by our original diagram. That's where we drew our force diagram. Part B is at the top of the screen, where we originally did our unit conversions from grams to kilograms. Then part C and D are on the bottom left of the screen, where we can actually add space to do those calculations.